continue on the, we'll start on the Chapter-14. Alright, so Chapter-14 is about chemical equilibrium. And this homework is the homework for the textbook we use, the third edition of Truth book. And you can see from the picture in this, on this slide, and these two lines represent the three lines, the blue line, red line, and together, and then the green line represent the concentration change as the time of the reaction. You can see at the beginning, that's assuming we don't have a concentration of HI, so that means we don't have the product. And so therefore the green line representing the HI, you can see at the beginning, the concentration is 0. As time goes on, the concentration of HI getting more and more, but after a certain time, it goes kind of to a plateau. Similarly, you can see the concentration of H2 and I2 represented by the red and the blue. The concentration gradually decreases. Similarly, after some time, and you can do some estimate. So the concentration, all the chemicals are not changing anymore. And at this stage, as we talk about in Chapter-13, usually the concentration of the product and the reactant don't have to be equal. So from this time on, we see our chemical reaction already at the state of equilibrium. So after this time on, the rate for the forward, so there are two rate and rate. And so these two rates are the same. And no matter these two rates, we see the forward rate and the reverse rate is elementary or not, but we know the going forward and going backward, the two rates are the same. Now this chapter and the next two chapters are those problems. How can we use some information to calculate those concentrations of different reactants, different products at equilibrium? And we can use some information also calculate what will be the ratio, what will be the relation between those concentrations. And there's a special relation between those concentrations, and we call that the equilibrium constant K. We're going to study those in details. So just some of those elementary, the so-called arrow conventions. So usually the chemists commonly use two kinds of arrows in the reaction to indicating the degree of completion of the reactions. A single arrow indicates all the reactant molecules are converted to product molecules at the end. Right. So this just relatively speaking, if you like see like in the next couple of chapters, some reactions. And in the general chemistry 1 class, we might use single arrow, like those precipitation reactions. If we take some of those silver, like 81 plus ion, and put some of those chloride ion, then we know it will produce like the silver chloride. And silver chloride, that reaction pretty much just going like forward, we usually say complete. So one example is if you take AG plus ion in like aqueous solution, plus chlorine ion, and in aqueous solution, and you produce AgCl, which is a solid. And this reaction in Chem1 versus this one arrow, and indicating the reaction complete. But in this chapter, we can see even those reactions, we think about usually have a very large K complete, but you still can calculate how much will be the reverse reactions. So just I think this is not absolutely true. You see, like all reactions are gone, but actually you still have some of those very very small percentage left over. So that's what we have this concept now. The double arrow you're going to use for the reactions. We are going to study in these next 3 chapters. So the double arrow, as we saw, yesterday's in chapter 13 class, the arrow pointing forward on top, which means the reaction going from left side to the right side. And similarly, the half arrow at the bottom indicating the reaction going from right to the left. And here we just use the two have the equal length. Sometimes those chemists also like to use, they have different lengths. So representing your reaction favors which side. Okay? Usually you will see something like this. If your reaction favors like the product side, favors the right side, you can draw a very long arrow pointing to the right, and draw a very small arrow pointing to the left. Right, so you will see a few of those graphs. Just read the graph carefully. So sometimes I might give you the concentration with time, and sometimes I will give you the rate of the reaction, the forward rate and reverse rate. So this graph is the same as the first graph we saw on the first page. So what we see is the product concentration increases, then become constant at equilibrium. Just as you measure yesterday in the lab, you see the freezing point. Sometimes it's not really a very sharp point you can identify. So similarly here, you see like which point is really your reaction reaching the equilibrium. It's kind of smoothly going from increases and decreases and constant, and you can do some of those estimates. And the product and the reactant in this slide are the usual signs. So usually when you write a chemical reaction, you will see the left side is our reactant, the right side is our product. But when you study these few chapters, actually you just you can see like either one side can be the reactant, or either the other side can be the product. You just have to indicate in reactant for what reaction, product for what reaction. So you can see the left side are the reactant. For the forward reaction, usually we'll see forward means going from left to the right. Okay, so we can estimate somewhere, sometime, or after some time, the equilibrium achieved. And you draw arrows from then on, the concentration not changing anymore, unless some of those disturbance. So we have the equilibrium there is kind of not changing, but some of those disturbance or some of those so-called stress can change your position of equilibrium. You apply a little bit like temperature, or change the volume a little bit, or add some of those reactant, take the reactant away, and depend on what we do, we'll study in details, and then your those curve will jumping up or come down. So for a while, then after some time, the reaction will make the line goes straight level again. Okay, now let's take a look at the rate. So how a chemical reaction reaches equilibrium, reaches equilibrium view from the rate. Now we have two dots, kind of dots. One the blue means forward, and then the red means reverse. So let's say at the beginning we don't have anything on the right side, means the forward reaction happens, reverse reaction going from right to the left, and not happen, and we'll have these two dots representing the initial rate of our system. Okay, so we have the red dot at the bottom, which means 0. There is no reverse reaction. And the blue dot on the top, that means the rate of the forward reaction is very high. And now this is second pair, which means after some time, you measure the rate again, and the forward rate decreases a little bit, and the reverse rate increases from 0 to some numbers, to some non-zero numbers. After another time, you measure again, and it continues a similar pattern, so more and more product produced. The concentration of the product increases. As we study in Chapter 13, most of the chemical reaction rate depend on the concentration. So if your concentration build up, increases, your rate increases. And vice versa, so the forward reaction, the concentration decreases and the rate decreases. So finally, these two should come together. Eventually, the reaction proceeds in the reverse reaction and the forward reaction at the same speed. So that at this time, equilibrium is established. Then you measure on, pretty much all the same. Any questions? You want to take it? Yeah, I think I put this on the iCampus, right? The lecture notes on the iCampus. Okay, now we go back to the concentration. Okay, now we have this. We have the concentration. We have the rate. So basically, we get some idea at equilibrium. Your concentration don't have to be the same, but at equilibrium, your forward rate and the backward rate are the same. And we see this region, after some time, we call that the equilibrium region. Before the time, it's non-equilibrium. One important relationship we can find out between those concentration of the reactant and the product is given by this equilibrium constant K. And the expression or the equation for the equilibrium constant K is the topic we need to study, and it depends on the reactants and the product state. So you can write those equations or write the expression, and then we can use the expression or the equation, and if I give you some numbers, you can do some of those calculations. So we know reactant or product in the chemical reaction have like 4 states. The 4th state is gas, aqueous, usually aqueous simply just AQ, solid, and liquid. So let's summarize here. So gas, you just abbreviate G, and solid will be S, and the liquid will be L. Okay, so when you write the expression or the equation for the equilibrium constant K, you only write the first, you only include those substance that has the first 2 states. And only included in K. Even though you still need the solid and the liquid to have the chemical reaction, but when you write the equation, okay, so this guy, we call it is the expression. Expression for K. And K have also sometimes have a different name. And for this one, you will say this is the KC. So depending on what we use. We know from Chapter-13 we have the angle bracket, which means molar concentration. So we have molar concentration for the reactant products, for the gas, or the aqueous solutions. You just say that is KC. Sometimes people also use the partial pressure for the reactant, for the product. Then you also call that KP. So this is for KC. And what's another is KP. So KP have a similar. And everything in KP, you will not see those pressure also for the liquid. You only see the pressure for the gas. I mean the pressure for the aqueous solution, for the liquid. Alright, so this is the concept called the equilibrium constant. And then later on you will also see another concept called the reaction quotient. Well, I think on the next slide you will see that. So the K is for those concentration after equilibrium. So you will have those kind of relation. Then before the equilibrium or after equilibrium, we have another concept called the reaction quotient. Reaction quotients have the same expression as the K, but the reaction quotient, you want to get to what is your reaction quotient, you don't have to use the concentration at equilibrium. Any point in the process of the chemical reaction, you will have the concentration for the product, have the concentration for the reactant. If you know what are their concentrations, you put it into an equation like this, so what you say, you get not always the equilibrium constant K, you always you know for sure you always get the reaction quotient. So then we know after the equilibrium, what you get from for the reaction quotient, you thought that might be k, might be not. If you get that number, and then I tell you that what you get is after this point of time of equilibrium, then your k and q are the same. Otherwise, your q and k it will be different. Okay, now first, so this is the equation for k, which is representing the relationship of those concentration or the partial pressure of some of those reactants and some of those products. Now we know this k, it will not change if you don't change the temperature. If you change the concentration of someone, and the reaction will be disturbing, and so then this is the kind of the nature of the reaction, and then the reaction will try to re-establish the equilibrium. After that, you still have the same k, even though all the number might scramble. So your HI on top may increases, and then these two numbers at the bottom also increases. So the end result, we still have the same number. Okay. Now at any point in the reaction, you have the so-called reaction quotient. The reaction quotient, we call that number that name, because it don't have to be at equilibrium. At any point, you can measure the concentration of the reactant, measure the concentration of the product, and you do a calculation, use the same equation as the equation for the k. And you get the so-called reaction quotient. So sometimes you can use the reaction quotient as a help, and to find out which direction your reaction will go. If I give you a k, and I give you a few number of those concentrations, and then if I ask you, is your reaction at equilibrium, or your reaction was going forward, or reaction going backward? So what you can do, you can just take those numbers for the concentration I give to you, and make a calculation. You see that is your reaction quotient. Then you compare the number you get, that's the reaction quotient Q, with the number I give to you. I said that is K. So then you see, this number you get for Q is the same number for K I give to you. If you find the two numbers the same, that means your reaction at equilibrium. Then otherwise, if your Q is larger than K, your reaction will going from right to the left. If the Q is smaller than K, your reaction will going from left to the right. So finally, sometime, maybe sooner or later, because depending on the reaction speed, and your Q and K will be the same. I mean your reaction will back to equilibrium. Okay? So keeping in mind, we have 4 states for the solid planes. You should only include the gas and aqueous solution in the equation or the expression for K and also for Q. So if I give you this reaction and indicating sulfur, as you see in the bottom, ignite, and it combines with O2, produce SO2. Okay, now if you want to write the equilibrium expression for this chemical reaction, even though you need sulfur for the chemical reaction, but in the expression for K, you don't see the concentration. You don't see that in the expression. Okay? The reason is you can put it in, and then you will take it out. What you get is sort of the constant. So the concentration of a solid and liquid are not changing. Even though their amount, how much you get, might change. So sort of that part of the solid in the chemical reaction. And what is the concentration of sulfur? You have 20 grams, or you have 2 grams, you will have the same concentration. You can calculate the concentration of pure sulfur by calculate the molar concentration by using density, find out in 1 milliliter how many grams, then change the gram into mole, then change the milliliter into liter, you divide, you get the concentration molarity. Right? That is the ratio. So that will never change. So if you initially put it in the equation, then it becomes kind of tedious. So you will move it all together to the side that has the k, and you finally get the equation like this.
So it's always going to be the products over the reactants?
Yeah. Always the product over reactant. Okay. And then later on you are doing some of those practice. Because the reactant retain the left side, the reactant, the right side product, sometimes you can write in a different way. So the reactant can going forward, can going backward. So going forward, the left side, and going backward, you can see those guys immediately on the right side, they will become reactant. Right now, another example is just these two examples. I think just want you to keep in mind. Solid and liquid never appears in the equilibrium expression, and neither in the reaction quotient Q. So you don't have to include in those pure solid and pure solid or those liquid, maybe not pure in solutions. You don't have included. Pure solid, pure liquid solution. You have to include them in the expressions. Right. So you have this ammonium solution and water that's unified, so that is liquid, and then you have the ammonium aqueous and OH aqueous. And similar reason as the last slide. So this water will not appear in the expression for K. So this reaction, you are going to see quite a few times later on in this chapter and in chapter 15, is the so-called acid-base reaction. Okay? Yeah. So we will see this in this example, and our base is and this guy, and our actual water becomes acid. Okay? So acid-base reaction will be the topic in the next couple chapters. Right. So now let's do some few practice. So the relationship between K and chemical equations. Right. Assuming in the following reactions, all the reactant products are in gaseous or aqueous state, when the reaction is written backward, then your equilibrium constant is inverted. So what that means, initially let's say we have A and B on the left side, and we have C and D on the right side. And now let's do a practice as what we do like in two examples. Assuming all those A, B, C are gas or equal solutions. So the K for the first one, for the first reaction, okay, on this side, initial equals, and let's write Kc, okay, use like the molarity, the concentration, and initial equals capital C, which means product C, and to the power of C. Okay. Then times the capital D to the power of little d. Then divide by the capital A to the power of little a, divided by concentration of B to the power of B, little b. So let's just use our convention, use our what we studied in 2 slides, 2 examples. Here we include everything, every substance, because every substance here is in gas or solution. So their concentration are changing. Right? Now use the similar convention. What will be the Kc? Let's say the Kc, we call this is the Kc prime. Okay? What about our Kc prime for the reaction as written as on this side? Similar convention. What do you put on the top?
Concentration of A.
Very good. So the concentration of A, capital A, to the power of A. Okay? And concentration of B to the power of B. Now you concentration of C to the concentration of C. Concentration of D and to D. Right? So now you can see clearly what is the relation between the K prime and Kc. Just inverse. So you can see in like the mathematical way, you can see Kc equals 1 over Kc prime. So this one, what sometimes call one manipulation. Okay, so this first manipulation is you write the reaction backward way. And then the K for the backward way reaction is the inverse of your initial forward K. We can see the K backward is the reciprocal of the K forward. So the next example is if you have the original, we call that the original equation, written as A plus B plus C, and this time you multiply your equation by some number. You see the 2 equations on the left side, we have A and B and C, and on the right side, we have 2A, 2B, and 2C. So we multiply every substance in the reaction by 2. Now you just rewrite a new equation for K for the reaction after you multiply. Right? What do you find out? You will see every concentration in the initial squared. You first write like something like this. Use our convention. You will take the concentration of the reactant and take the coefficient as the power. Alright, so then we'll use the math rule you already saw in chapter 13. Okay? So if every number have a same power, and you can pull the power out and as a power for everyone. Now in this equation, every concentration have a power 2. So even though A, B, and C are different, but they all have a 2. So what you can do, you can just take the 2 out and leave those A, B, and C inside. And then you can see what is inside this bracket is actually our K original. Our original K have the expression that is inside the angle bracket. Okay, so that means your K new equals what is the relation between your K new and K original? Yeah, you take the K original and square it, you get the K new. This is just my example. This square comes from you multiply the original equation by 2. Right? So then in general you can say if you multiply your equation not by 2, by some other numbers. Right? Whatever number you use to multiply your original equation to get the new equation, you will use that number as the power for your K, for a new K. Right? So therefore we come out with this equation. Okay? We don't use 2 or 3, and we are seeing the number n. Obviously, your n can be any number. Okay? Can be 2, like what we see here. Okay? So n can be 2, any number. Okay? Or can be 3. Okay? Or let's say it can be 1/2. If you multiply your equation by 1/2, that means you divide your equation by 2. If you divide the equation by 2, then your new K will be like the square root over the old K. So just know the n can be any number. Okay, now we let's say before this one we know how to reverse our equation, how to multiply or divide our equation by some numbers. Now here we'll see how we adding 2 equations together. So we have equation 1 and equation 2. Right? So then we have another equation. Maybe I should call this equation 3. So this is the equation 3. Now the equation 3, if you can check that very easy. How can we get equation 3 from equation 1 and equation 2? How can we get equation 3 from equation 1 and equation 2? That's sum. Okay? So we did that practice like in chapter 13, the last section mechanism. Okay? And you take the A, for example, A and A. Okay? And so this arrow I use to represent this arrow. and little b and capital B. Then you have this b and b, the same convention, c and capital C. Right? So when you add in these two equations together, let's write that sum, and you get a little a and c capital C. And that is the one we saw on this side. Right? Now let's write the equation for all the three reactions. I mean, write the equation for the k for all the three reactions. Keeping in mind, we know the equation here, let me still name this 3. Equation 3 is coming from the sum of 1 and 2. Then let's see the relation between this, between those k. Let's call that K1 for your reaction 1. Again, I think I will write some. We're assuming in all those reactions, A, B, or C, they are either in gas state or the aqueous solutions. So you get K1 like this. Right? So similarly, what will be the K2? Or C over power C and then divided by B to the power B. Right? Similarly, you will write an equation for the K for reaction 3. Right? Let's write an expression for the K for reaction 3. It looks like that. Right? There's some relation between these 3k, even though not that straightforward. Anyway, find out the relation between 3k. The book and my lecture notes give the little different way. Yeah.
Is it K2 times K1?
Yeah, how do you find that? K2 times K1 is what? K2 times K1 will give you what equals what?
Oh, K new.
K new. Yeah. So that's the one very good way to find out the relationship between K1, K2, and K new. You take a K1 multiply K2, right? So K1 times K2. And you just come up with an idea like that, and you just take what is the equation for K1. Equation for K1 is B to the power B and A to the power A. So that's K1. Then you say K1 times K2. Then you say what is K2? You say C to the C and then B to the B. So now why this one equals K new? K new, that means you have a C on the top and A at the denominator. How can this equation I write the same as this? You cut out the B. Now if you want to go the other way, you don't like check, you don't take the K1 times K2, you just take the K new, and you will do something like this. You can just multiply KB on the top, or divide KB at the bottom, and then this also comes out, and then that also gives you K1 times K2. Right. So anyhow, so this is the relation between the K, between the K's. If you add like two equations. I think this pattern can go like even you add in three equations. If you add three equations, you have 3k originally, then you will multiply all the 3k. Now let's use some of the real number for some of the real equations and do some of the practice of calculations. Okay, now do some practice, see if you can use what you just learned. I think we learned 3 manipulations. We learned reverse the equation, you will invert the k, and then you multiply some number to the equation. You should take the number you multiply as the power for your new k. Then we add. If you add into equation, you multiply the k. You might, for this problem, you might have to combine those 3 manipulations, like use one manipulation then followed by another one. Right? I think you cannot use simply reverse equation get the new equation. Do you get some number? Yeah, that's what I get. 5.2. Yeah. 5.2 times 10 to the negative 5. You get it? Excellent. Very good. So just compare the new equation you want the k, right, with like the old one. Yeah, 5.19, 5.2. What do you get? You get some number for this? Try it.
No.
Get something? Okay. See, you compare the equation at the bottom of the new one. So what it looks like? Looks like the original one, the old one, you have the N2 and H2, and also N3. So does the new one, right? But this switch place. So when you think about that 3 manipulation, you can switch place so the one on the right side can go to on the left side. What is there?
Still working on it.
Get some number?
Not yet.
What do you get? Very good. Right up. Right, what you just did. Here's the idea. So if you inverse, you are just reciprocal of the k. You know that inverse because initial n3 is on the right, not because on the left. Not only that, you can see that the coefficient also big one. Okay, so here's 2, right? So that's the original one. But in the new one, the 2 is not 2 anymore. The 2 become 1, right? So that how can you change 2 become 1? Multiply by 1 over 2, right? Yeah. So, then the equation. So if you multiply the equation by 1 over 2, then you will use this number 1 over 2, right? So you will use this number 1 over 2. You see like in one of those, in one of the manipulation, this is like this one. So if you multiply this equation by 2, then you will see this becomes 2. This becomes 2. So this 2 is actually the one, the number you use to the multiplication.
So you see that NH3, it's on our reaction side now?
This time, what number do you use to multiply?
And you see it's not.
One half.
So NH3 is in the first one, you have 1 in the second one, so you can square root of it.
Yeah. And that's your daily number, right?
Yeah.
I think that here will be 1.
Was 4
Here will be 1. Yeah, here is the 2 power 1 half. Yeah, also here.
Because we switched there.
Right, so it's
1 over.
But how you do this? You will see what is looks like in this equation. You want to find the k. If you see the k, like the equation you want to find the k for the n-3 on the left side, and then the n-3 on the right side. That means you get this new equation by reverse your old equation. And then, well, according to one rule, if you reverse your equation, like the way it's written, you change the right to the left, and your k will become the reciprocal. So that's one manipulation.
Yeah, I just started like that.
Yeah, one over the k takes some. So then, not only that, you compare the one, not only you switch the NH3 from the right to the left, the coefficient also change. See the coefficient like the new equation? You don't have the 2 NH3, you only have 1. And initially those N2 and H2 is 1 and 3, that become 1 half and 3 half. So that tell you also like did another manipulation. That means you take the which one you did first on the matter. That means you divide the equation by 2, or you multiply the equation by 1 half. So then you will see if you reverse 1, you will that means 1 over k. If you divide by some number or multiply by some number, you use number as power. To the power 1 half. Welcome. What do you think?
Since the energy version is I make it negative, right?
Not negative. You inverse, reciprocal. That means if everything is still the same, you just but right now everything is not the same. But you do step by step. One thing is not the same is that you said the right side is on the left side. If that happens, you will simply take the initial k and do a reciprocal. That means 1 divided by that k.
So
One divided by the k.
Okay.
Yeah.
Okay.
So that will be the partial result.
It was the 1/2, when the 1/2 is divided, or I make it a exponent.
This will exponent to everything, to the top, to the bottom, to the top, to the bottom.
3/2 exponent again.
No, you get all those by like multiply that initial equation by 1/2. So the 1/2 is the only thing we use in the multiplication. You know, to the power. You use this number multiply the equation to get the new equation. Then you will use this number as power for your case. So you will just put everything in the bracket. Yeah, then just one power, one power. Then just erase all those.
So what's 3/2?
3/2 is what you get by taking 3 divided by 2. You see that 1/2 is what you get by taking 1 divided by 2. And that 1 in front of the ammonia is you take 2 divided by 2. So everyone is divided by 2. So even though the numbers is different, but what they come from all divided by 2.
So once I do this, that should be done.
Yeah, so that's the number.
And the sparkling voltage doesn't occur. That's my calculator. I need that calculator.
Let's see, how you just compare how you get this equation, from this equation. What's the difference between these two? You divide by 2, what else is different?
It comes from
Yeah,
in front
so
of
you
you.
do 2 things. If you divide by 2, that means your k new will equal something that's over power 1/2.
That's what I've heard.
In square root.
So
In
it's
square
like,
root on root. But then, you don't want to square root of the initial one, so the initial, you get this new one from the initial one by reverse. So you don't see this one square
that
root.
would be 2.
But this one is even square root, that means you just divide it by 2.
Yes, okay.
But you don't only divide it by 2, you also reverse.
So I third and. Well, that would be the same. Just third.
Your first, you need like a first square root, right?
Okay.
Or then you just take the inward, take the reciprocal.
Oh, like if you were to make them all one, I make change.
Yeah, we use, yeah.
So.
Okay, any questions?
Yeah.
Yeah, so that's, yeah. We have to, alright, so you, for those kind of problem, you just compare the new equation, new reaction with the old reaction, see what's the difference, right? Then you will see how can you get the difference, new one from the old one, from the original one, right? And then you are checking each step you make a difference, that something happened to your cake, right? It's similar like that. You see what happened to the new equation is compared with the old one, you invert it. Not only invert it, you divide by 2. What I did is step by step, right? So I compare like this new one. I see compare the new one with the old one. If I don't see if I don't change the number for the coefficient, I see that you simply take the right side become left side, right? If that happens, you can see this P new. So I call this P new for this new equation is 1 over the old k. So this step is clear, right? Now your purpose is just do like step by step, and from the given one, from the initial one, all the way to that. So what do you do next? How can you change this one into that one? How you change this one from this? Or multiply some number, or divide some number? about if you take this equation, if you take this equation here and multiply every those coefficients or every those substance by one or two, huh? Then you will get the one on the top. Any questions? So now, if you do this one, if you do this equation, which means right now you are going to multiply by 1/2, right? You get it? If you multiply this equation by 1/2, what do we mean by that? I think what we mean by that is you will put this equation in a bracket, then you do something like this. Okay. Now this means you are going to multiply this one onto this 3, and multiply this one onto someone here. There's not seems nothing there, but nevertheless what? And you multiply this onto this. So if you take this 1/2 and multiply on every coefficient, and that's what we mean. So when we write something like you multiply this by 1/2, that means you multiply everyone by 1/2, right? So then you get the equation on the top. Then according to the rule, if you do multiplication and multiply the equation by some number, now your key will be your key for your new equation. Your key for your new equation, that means for this one is the square root. Right, then just use your calculator and find out the number, which is 5.2 times 10 to the -5. Alright, so now try to find out the key for this new equation. Get some number? What do you got? Yeah, 2.067, right? 2.067. You want to 2.1. Two point zero one, 2.1?
Yeah.
Yeah, very good. So this is from your practice, right? You should see how you get the new one from the old one.
This, yeah.
You get 2.1 times negative 13. You get the same? There you go, 2.067. Yeah, that's better. 2.1, very good, very good. At this time, you do step by step, one time. Whenever you do the equation, you do something to the k. Okay? You get 2.1? Yeah. You got better last.
Whatever numbers are multiplied.
Okay, any questions?
Good.
Get it? You just see it step by step, right? So how can you change from, okay, that's good, but not only that,
Oh, I have
you have to multiply, you multiply the equation by some number to get the new equation, right?
yes.
If you use some number multiply the equation, you will use the number as power. So what number you use to multiply the equation, you reverse first, and then you multiply the reverse equation by some number to get the one at the bottom.
How do you get the number? That's what I need help with. How do you
You get a number by see to the coefficient.
Okay.
See in the O1 the coefficient for CO2 is what?
2.
For CO2. What is the coefficient? What is the number in front of CO2?
On the first one?
Yeah. 1.
1.
Then what is the number for the O1 for CO2?
2.
So how can you get 1 from 2? You multiply, you say I add 1, but you don't add 1. You multiply by 2. Don't worry, yeah. Oh, you can, yeah. So that means you multiply the equation. What we're trying to do first, according to what you did, you reverse first. And then after you reverse, you multiply by 2.
Okay.
So then you do each step. You do something to the equation, you will do something to the k. So then what do you do to the k? You don't do all the way the same, because you reverse the equation, you are reciprocal of the k. If you multiply the equation by 2, you don't multiply the k by 2. You take the power, use the 2 and power.
So I'll put it to the power.
Yeah, you take the power 2. So you are right.
Okay.
I mean, I'm encouraging you.
Anybody? You not hear what I said? This step by step, very good. So you take this one first, the inward, right? And then when you inward, you will receive for the k. And then you compare, see how can you go this one to this. You multiply everyone by 2. Then you don't, yeah, very good. Then you don't like simply take the number you multiply the equation, multiply the k. So the number you use to multiply the equation, you can go to the power. Yeah, very good. Wow. That's the best way to learn.
This one sounds like what the thing
Use the calculator.
No, it's just really asking the wrong answer, so I reset the whole thing.
Sometimes they get the use right, but
When we take our test exams, do we have to use like a
the test I give to you, you can use your calculator. I think on the final, the department have the calculator very similar to yours.
Yeah, it's like the little one, right?
Yeah, 35 or 35. Yeah, very similar to mine.
Oh, it's
Yeah.
like the gravel, whatever it's called. Paris? Yeah, it sounds. That's like my favorite Pokemon. Level 100, like.
Alright, so we said we have a 2k minus kc minus kp. So sometimes equilibrium constant for reaction in more gases, the concentration of gas in a mixture is proportional to its partial pressure as with what we learned in Chapter 5 in Chem 1. So therefore, the equilibrium constant can be expressed as the ratio of the partial pressures of the gases. For example, if you have this general equation, A, B, C, D are gas, so then your equilibrium constant can be expressed as following. So you will see, you still can use the initial Kc, okay? You still can use like those molarities. Now in addition to that, you can get a new one. The new one will be the Kp. So the difference between Kp and Kc will be some of those topics that you can see, like you can have the, on the exam or on the quiz. So the Pc and C and Pd and D. Now you know all of the P means partial pressure. Okay, so there is an equation between Kp and Kc. Okay, so just a few notes. In calculating Kp, the partial pressure are always in atm. In calculating Kc, the concentration is always in molarity. Usually the Kp and Kc are not the same number. For the same equation, usually they are not the same number. Unless we will see there is one like those type of equation, and you calculate the delta n is 0. Now with the delta n, and you see the next paragraph, delta n is more difference between the more of the gaseous substance in the product and subtracting by the more of the gaseous reactants. So that's so-called delta n. So Kp equals Kc times RT to the power of delta n. Okay, so I will not go through like the derivation, how you get this equation. I will simply give you like an equation that probably will help you to memorize. Okay? So you know that PV equals N, R, and T, gas law. Okay? Now you rewrite this equation, so P equals N divided by V times R and T. How I get the one on the second line? Initially have PV equals nRT. How I get P equals N divided by V and RT? Okay? How I get the equation? Initially this equation everyone knows the ideal equation, ideal gas equation. Okay? So how you get this one from that? Yeah, you just divide the way. Okay? Now you also remember what is the definition of the molarity? Molarity equals what? Mole over volume or liter, liter or volume. So the initial definition for this molarity is like this. So this is liter of a solution. Well, gas is a perfect example of a solution because gas always makes homogeneously. So therefore, we'll write P equals M times R and T. So where does the M come from? N is more. You can clarify. N is how much more? Okay? And the weight is in liters. And that will give you some like those hints, and you can memorize what is the relation between Kp and Kc. Okay? So you will see Kp, well, this is P, so therefore Kp, and this one is used in Kc, so therefore Kp equals Kc, and then R. But this is only for one substance. How many of those R, how many of those RT, depend on what is the difference between those coefficient of the product and the coefficient of the gas reactant. So I think quickly you will see the delta N is the difference between the number of more of gaseous products and the more of gaseous reactant. Any questions? Now do a few practice. Find out the delta N. that means you just use the coefficient for the gas. You find the difference between those gaseous coefficient and the reactant, the product separated by reactant. Okay, so what is the delta N for the first one? 0. You have two gas on the right side. You're going to take how much gas on the right side and subtracting by how many gas those coefficient on the left side. What about the second one? -1. Very good. And the third one? 1, positive 1. And the last one? -3. Alright, so we said this is 0. Let's see, look at these. Delta N. So this one is 0. Okay. How do you get 0? See, 2 minus 2 equals 0. That is, these two come from this. Okay? Now these other two come from 1 plus 1. 1 plus 1 gives 2. 1 plus 1 is 2. Now the second equation has delta N instead equals -1. Right? So where does -1 come from? Come from 2 minus, and these 2 come from this. Okay, so these 2, let me just use that, use. Okay, so delta N equals, the first one is 0. 0 because 2 minus 2 is 0. So this 2, and this 2. Okay. Now here this 2 is 1 plus 1. 1 plus 1. Right. So then this -1 and positive 1, -3. Any questions? Now even do a practice, right? You still remember the equation between K and Kc. When you see that equation, it has R in it, and so R equals 0.08206, and you see the equation has T, and T should be in kelvins. It should be 25 plus 273 equals 298K. So use these two numbers in that equation, just see what equation you use, right? take this number multiply, and then take 2 to the negative 1 power, and or you can just yeah, do that one first. By this number, yeah, so you all can do that. You can just take this number divided by whatever this number. Then we get, okay, and we want the second, 202 times that divided by, yeah, that's it. Probably, the R probably not, because I assume you don't know the R, like the, just sometimes the R is 0.08206, sometimes 8.314. The rule is something like this. When you see those kind of calculation, like the pressure, something with has the pressure and volume in it, you just use 0.08206. When you see like those calculation with energy in it, how many joule, how many kilojoules, you will use that 8.314. What do you get? That was right. Yeah, 5 pounds.
Yeah.
Yeah. And it's positive 13. Yeah. You get that? Yeah, yeah. Very good. Very good. Mm-hmm. Don't forget, I think there is a number to the power, right? So you have this 91. No. See what you see, you have this equation right. This KC equals let's see what's the initial equation? The equation KP equals this KC times this number. So therefore, this kind of opposite, right? This is the opposite. Yeah, here you go. So then you want to get the KC, you want to divide this out. You do divide KC, you divide this out. So keep the KC, right? Yeah. So keep the KC. Yeah. I think that this number looks okay, but I don't remember 5.34. Very good. You know your lecture notes probably live in details. Don't just thinking about it. When you see something like you feel like new, or you just write it down. Right?
Okay.
So that's the usual way of learning. The new things. You write it, so you accumulate. You get 5 on something and you go to 30? Yeah. What do you get? Excellent. Yeah. Good. Yes. Yeah. Very good. I think like most of you get the concept, and just remember this equation and remember the way of draw line.
Yeah.
So you just dive down. Let's see the result. You can back check and see if that's okay. That is right. Put it back into the equation like what you initially get for the KC for, and then you will find out that you get the same KP. Alright, so those are a few calculations about it's pretty much like a manipulation those k. Okay? Now, once you have the k, or if I have some other numbers, you can really from the concentration to get the k. Right? You can get the k from our equation, or you can get the concentration from your equation from your equilibrium concentration. Just keep in mind, those concentration in the calculation for the k should be at equilibrium. So if I give you some of those concentration, if I don't tell you that it's at equilibrium, you can put it into the equation, or what you get, you will call that you don't know for sure that it's k. And for sure you will see the so-called reaction quotient. Now this question tells you we have this equilibrium mixture. So what this tell you is all those given concentration equilibrium are at equilibrium. So they don't have to equal. So in general they don't have to equal, but you know the concept is at equilibrium. That means if you have the reaction mixture like that, you put that in a good place, don't like disturbing, and the concentration will be always those. So therefore you can write up, when you do a practice, you need the equation or the expression for k. So what is the equation for k for this reaction? So starting from that. Okay, so I think I recommend you first write the equation for the k, and then you will just plug in those numbers because those numbers are all at equilibrium. So find out the equation for the k, or the expression for the k first. The k not given to you, and the number not given to you, also the equation not given to you, right? You have to find what is the equation for k. K equals what times what by what, right? So usually the product on the top and right hand at the bottom, and you only including those concentration for the gas and the concentration for the aqueous solution. On the O, then you read the opposite. You will see you read the opposite. That's okay, so then once you get the Q, you just flip it over. No. What I get? Power 2? That was reasonable. You know, the 8 to 3 is the third power. Yeah? No, it's power. So use the coefficient and power. Later on, you can use the coefficient as multiply or multiply when you see how many change. Right? So right now, when you're calculating the k, just use the coefficient of power. 0.02. See, you should remember how you write the equation for the k. Very good. Yeah, that's it. So you have that first power, third power, second power, and that comes from the coefficient. Yeah, very good. So sometimes it's very easy to like see what number for what? Sometimes you are like do some mistake, like you find 5, so it means it's dynamical for H2 and so on, right? So when you have the equation, you go just step by step, then you just read the equation carefully. Yeah. All right, did you get 102? What do you get 102?
Yeah, that would be like.
Yeah, so I don't know.
Yeah, I will parentheses, I just don't see division symbol, which is probably.
102?
I just think it's remember.
Get it? 0.02? What is the equation for K? For this chemical reaction equation? How you write K? How you write the equation for K? Right, something like that, right? So you take those products on the top, and you take the coefficient for the gas or the aqueous solutions at power. So the equation for K equals the angle bracket of H2 to the third power. You have to write. If you don't write, you are. Usually you will write something like this. So you write K, right, or Kc equals some of those products on top. This in general, then just in details, what product to what power. So we have one product is H2. See the coefficient is 3, so 3, right? Am I right? One product is H2, right? What other product? C2, H2. And then what other one?
CH4 and S2.
CH4. And your power is 2. You include all the 3 because they are all in gas. Okay? Understand? See the states they are all gas. If you have something is solid or liquid, don't put them in the equation.
I feel like manly, not like we have a fist fight.
The same equation, but this time we are going to find out something different. So you already know the K at that temperature is 0.02. Now we are going to see at the same temperature 1700 Celsius. So I think we still need to start with the equation for K. Right? You still need the equation for K. In the next few chapters, this chapter and next 2 chapters, pretty much that's where we can make a starting point. And you have to recognize sooner or later when you use it, you'll see what's your equation for K. get something, I think that in the right is K, right? You still have the similar, well, this is H2 to the third power, right?
Alright.
Okay, you still have the same equation. You still have the same equation, just plug in what you know, find out what you don't know. Okay. So yes, you have K, you still have same K, that's equation sum from, right?
Yeah.
So this is K, and this is the C2, H2.
Yeah.
The power is 1, I have H2 power 3, and this number is for the C4 power 2. Excellent. Yeah. Then you can do that. That is probably a little tedious, or you can just multiply this number over first, then divide by this number, then just take the cube root.
Oh, that's right.
Oh, I thought you said you just cube root for everything
Well,
first.
no, after I did that, I actually heard that you but.
You just dated it.
So you have this one, you get the number, and then you
Yeah, then I divided this one over and down by itself.
Yeah.
Yeah, but that doesn't use that. Like I've had figured
on the 07, what? Sorry? On the 07. You get on the 07 one?
Sorry, I don't. Yeah. Use for the.
Alright, so now those are the so this you don't know how to take the root, cubic root. Yes. Yes. Oh, what's wrong? What is wrong? This is strange. 0.035 and 0.035. What are those numbers? That is for C2, right? 0.05 for the C4, from C4. Okay. So that. I guess. Oh, you don't see? Okay. Yeah. Let's check again. So you take 0.02 times 0.05 squared. Okay. Then divide by 0.05. Now let's make it very yeah, that's the pure root. I think we need one number. Just check carefully, see if you can. On what other number? There's a 0.025. I changed the number. No, this is a spread.
If I have an A, now what do I do to find out?
What did you get? 0.025?
It's the same equation, but you have to change CH4 down to 0.025 instead of 0.05, and you just plug all those in and separate streets and you don't know it, and then just solve it.
And you said you plug what in for C2, H4?
No, C2H4 is the same as it was before. It's just that this time I changed the CH4 to CH4. You see it's 0.025, so you put it like a one less half there.
Now you put 0.25.
This is beautiful. Perfect, right? So then just plug it in. What number from here? Don't change something yet.
And then you just do like
So
solve.
just put something in whatever you know, right? You know, okay, the 0.025. This becomes the number on the 0.025. I think what I think from is to trade them to
Yeah, I just love it. Now I'm just at a level 5. You go ham at the gym. about that. We'll see about it. We can just evolve. We can just evolve.
Least aesthetic program.
Exactly.
Are you at college yet?
So,
I haven't graded.
this one,
I haven't graded.
that's your first name or last name?
Yeah.
First name?
Good enough for cool.
Yeah, right.
Yeah, we did it. Such a-
This one's too. Catching 1,000 wheels.
Okay, so let's find the 071, right?
There's so much experience in here.
All right. So consider this, you also like remember, I think like a couple questions ago, I mentioned, those concentrations should be at equilibrium. So you read the question carefully, if I don't tell you it's equilibrium, you cannot know like what you get is K. Okay? Now what is this new about this one? This is we go back. We have the K. This is actually very similar as the last one. Oh yeah, this question I was hesitate whether I should put this one or not, like this for the weekend, because we already have the one like before this one. I thought probably we'll do it again because I saw before like some other cars always have some those difficult to find those. To solve those kind of problems. You solve the equation only for the CO2, right? CO2 on the top, and you multiply that and divided by the concentration. That concentration CH4. So what is CH4? CF4. CF4, CP4? CF4, right?
Yeah.
CF4 is what? The product?
Yeah.
Why is too many steps? Probably not right. So you want to get a CO2, right? So this you can actually this is right. And you want to get a CO2. I think I will just multiply this many more and divide by
Have 5.
Yeah.
Yeah, 5
Okay,
bucks.
good. So then we
Yeah.
get.
Yeah. This one's nice updated.
This is goes in 2.5 square, and this 2 is 2. What about the,
Yeah, I saw that. You're like,
I think the meter will be
walking
some.
around.
What, oh yeah. CO4 have a square.
Even sticks to that. Yeah, buddy.
Maybe we'll get a break.
That's,
We should get a break halfway.
you wanna find out this one, right?
So maybe I would just walk through that.
So do we have to like modify it?
I think if you have K, you don't have to modify any of those, right? What we did before, modify this one, like divide by some numbers or reverse it, is because we have a new equation different than this one. So in this question, we only have one equation, so this is the only equation. And so we have that, I think as what you did is,
But you can't use the terms because they're not the same as an equation.
what equation?
And that's
Oh, I see. Yeah, I make a mistake. This is COF2. I had a CO2F2. Oh, very good. Oh, I see. Yeah, so if they are not the same, then use that. So this is C.
You have to, this is just as close as it is, so not the same. And this is
This is C.
So then I just put this, multiply it by that, to the second power. And then I didn't multiply it in that.
So,
case.
yeah, so
Like,
that-
I multiply this.
You get ball.
Right,
I mean, this-
carrot this.
So that's CO2F2 and CO2
Multiply this.
CL4. That's perfect.
No, I multiplied all,
So
I just
then,
did 2
then-
times
then-
this square here on.
Okay, so what's the number? I think that's a very similar calculation. Huh? 0.11 something, right? 1.1. Okay, any questions? I said this is the same as the last one. Yes. Good. So that I'm glad that I did this question again. When you were looking at it, I sent the letter note. I was talking about no. That's a good practice. So you just write the equation for the key first.
I'm bad against Taurus. Whatever, Taurus.
Because the structure is the same, but the same. This is probably the same as the last one.
I always
For sex, because they're not.
Gala.
Oh, we have a lab. Yeah, the lab you can turn in when we like when we not.
Doesn't do anything.
No. However, you forget some.
I might do that at break.
This is not bad. 2 times this square, then divided by that. Do we have anything for CO2? Nothing for CO2 in the equation, right? Yeah, that's like the root square or something, right?
I know, I feel that.
You see like people who like write down like
Times
increase in like bike sales. Because like they like bought bikes just for the game.
Oh, I
That'll help
see.
you hatch an egg.
2.
Huh?
That'll help you hatch an egg.
Oh yeah.
You go under 70 miles per hour.
Oh,
That's
wow.
how you're just walking, yeah.
255.
My life just gets so much better.
Yeah, it's like in the game, you know, you try to
Yeah.
find the longest stretches, and then you just bike back.
Oh, you
Do
can
that
find
for
cars
life.
here slowly.
Yeah. Well, you could, but like most neighborhoods are.
Or like you just attach it to your fan.
Or what?
You could attach it to your fan.
No, does it work with it?
It works.
GPS.
It works. I've seen it done. It works.
Right, so the next, starting from this example,
Just upgrade
this,
it.
I said this is IC terror.
I prefer to raise your scooter now. Excuse me.
I mean, you can turn it.
So the IC terror procedures, that's starting one of few of those, and we will just do the lab. This lab is on the laptop. Okay, so you can see read this question carefully, and you have a reaction mixture. Initially, only have this. I didn't tell you it's equilibrium. So then at equilibrium, you have this concentration. Okay? So then what you want to find out is the value of the equilibrium constant. So this kind of continue with what we did in the last two examples. You want to find the K, you need the concentration for the at equilibrium. But this question only gives you one concentration at equilibrium. You understand? So you need all the concentration at equilibrium. So what you do is just make so-called IC table. Sometimes we cannot really need that. So KC is 26, and what you do just CO, which is gas, so therefore in the equation, and 2 is 2, and C is 3 OH, so that's also gas. I, and you know what is I, what is C, what is E.
Initial change
And equilibrium. So E is equilibrium. So you just usually just make a list, okay? Leaving space, and then you can fill out the table. Okay? I means initial. Okay? C means change. So E is the equilibrium. If I don't give you any like those compound initial concentrations, that means they are 0. Right? So initial concentration for CO is 0.500. I will skip the unit capital M, but we don't have a space. Right? And H2 is 1.00. See the initial? This initial gives you the I. Okay? Initial is I. The problem did not tell you initial what is your methanol. C is 3OH. We don't have a number for this. And you will, after a few problems, you know this is 0. If I don't give a number, that means 0. So then you also given at the equilibrium, so the CO is become 0.150. Right? And usually you can use some common sense to figure out this reaction, like something happened to this reaction going one way to have this equilibrium. This equilibrium concentration is 0.15, at the beginning is 0.5. So by thinking about that, you know how this reaction reach the equilibrium. Going from the left to the right, or going from right to the left? Going from left to the right. When you're going from left to right, So those guys on the left side, the concentration decreases, and those on the right side increases. So then when we know this region going from left to the right, and then the change for those guys on the left probably negative, because they are decreasing, and those change for the right on the right side probably plus. So then how you know the change? You just take the E number minus the I number. So this change here is 0.350. So then you can use the coefficient. Remember those what we learned in the Chem 1. Use the coefficient as a ratio, as a conversion ratio, convert this change into the change of all the others. So this guy have a negative 0.35 change. What will be the change for the 82?
0.7.
Very good. Negative 0.7. Well, twice of the change, right? Because you use every one of CO, you will use 282. So this becomes negative 0.700. Any question?
Can you explain it again? Why it's 9.0?
Because you have this coefficient 2 here.
Okay.
So all you can do a conversion like this, right? So from the equation you get the mole ratio, right? So for every 1 mole of CO, there is 2 mole of H2, right? Now this change, this negative 0.35 is about molarity, but molarity is proportional to your mole. Right? So this negative 0.350, so even though it's a capital M, but you know capital M means the mole divided by the liters. The liters are not changing, right? So the liters not changing, you can just convert in the mole. And so therefore you can see this is the molarity of CO, which means mole of CO divided by volume. So on the top you will have the mole, so this comes out. Very good. So then what is the change, what will be the changing for the product?
0.93.
Well, let's see, probably, let's see. What is our product? What is the product going forward? C3OH, right? So C3OH is a product. If the reactant concentration decreases, at least you will know what will happen to the concentration of CH3OH. It will be positive or negative. The concentration of the methanol for increases or for decreases. The concentration of this guy. You need, right now it's 0, right? If it's 0, if something is 0 in your equation, you will never have the equilibrium. So at the equilibrium, you will not have 0. So we're plus, right? Probably positive. Now positive how much? Depends on the coefficient. If the coefficient 1 here, right? So that means you use one of the CO, you will produce one of this. Now how many CO do you use? 0.35. Right? So the positive 0.35. Very good. Okay. Now once you have the initial 0, you have the change, and you get the change by subtracting this number with that number. Right? So if you don't like notice how did I get this negative 0.35 from here, so I initially get 0.150 minus 0.500, I get a negative 0.350. So this is how I get this number here. By using the initial information, because initially we only have this number, this number, this number. So those are the information given to you, right? You could like kind of make this IC table, and you just populate this table with those information given to you, Then you figure out from this information what you can do. So you have this number subtracting, you get this negative 0.354, 0.35. Then you're doing, okay, if this is negative, this is also negative, but they are all relative. But their number may be not the same. This is negative 0.35, so this is twice. How do you do twice? Because you use, for each one of these, you use 2 of these.
I'm sorry, not arguing. Probably already answered this, but why is it a positive 0.35?
Okay, good.
Just because it's on the other side?
Because on the other side.
Okay,
So the change for those guys on the other side will be always the opposite.
I got you.
Now, Amanda said that at equilibrium, this concentration will be also like 0.35. How you get that? I'm doing one step forward. I will show you how you get this number. So this kind of the equation. That means if you have the initial, you have the change, add it together, you get this. If you have the equilibrium and initial, you subtract, you get this. So these 3 numbers are always like that, right? And that's why what Amanda said, you take 0 plus this, and you will get 0.350. Right? So now what will be the number here? Once we get all these 3 numbers here on the line of E, and then we will get what we want to find out. The equilibrium constant. You have to use those concentration and equilibrium. So we have 2 numbers now. Now what with this number? 3. Just not literally add them together. Just sum them together. So you do a sum. You sum 1 with negative 0.7, so you get 0.3. Now this line, like on the line, those 3 numbers on the line with E, that means the concentration at equilibrium. Those are the numbers you're going to use to find the K.
I plus C will always equal
Yeah, you can change I plus C always E, or E minus I always C. Then those C and the C might be different. Okay? First of all, those C for the reactant, if the C for the reactant is negative, then your C for the product will be positive. Right? Not always your C for your reactant is negative. Sometimes your C for your product is negative. Then all the C for the reactant will be positive. Alright, so we don't need those numbers now, and we just need the equation for the K. Then we will just put those numbers in for the K. Right? So what is the equation for K for this reaction?
concentration 0.350.
Okay, that first probably timing, right?
Yeah.
Probably that first use the compound formula. So K will equals right here. K equals water concentration divided by water concentration and so on. Very good. CH3OH. So you include that because that you get. Yeah.
Instead of CH3OH, how do we know that the initial concentration is 0?
That's a good question. Okay. So you see, like what I tell you initially, right? Initially have this, which is the CO, and the other one is the H2. This is kind of like the usual like a convention. So the proper usually give it to you what is in there. If don't give it to you, then it means 0. Okay, so the question is, I think that's a common question. So most of the time you will see, I did not see anything initially. What is the concentration of CH3OH? That means it's 0. You kind of those people who write those questions, whether they are lazy or not, they just say if I don't give it to you, that means it's 0. Alright. So this will be the angle bracket, and then divided by what?
Concentration of CO
Very good. Concentration of CO
times the concentration
Yeah, yeah. And don't forget those coefficients, okay? And the coefficient is very important. And also you have to make sure, what you put in the equation is only gas or aqueous. You don't put those L or S in the equation. Very good. So that next step, you apply those numbers in, and you get 0.350 divided by what? 0.150. Then just use bracket easy to see. Don't use like the multiply. 0.300 and what? Square. Okay? Yeah. So it's very basic. So here we learn those techniques, and you're going to use this technique as well as IC table many times in the next 3 chapters, including this one. Now you can do a calculation and get a K.
26.
26. So the next few slides, I just write down the lecture notes. So in case you want to study sometime like before the class, always good to have it, study those lecture notes and read the book before the class. Okay. And so then we'll just do the lab now. Okay. Okay, so today's lab, I sent you the email, right? Last night. Those are the procedures. And so you are doing on the laptop. Laptop in the back on the chart. So just each one of you can take my laptop. Before you take it out, see what it looks like. We finish the experiment, you just put them back the same way you take them out. Okay? Yeah, each one of you get your own. Have like your laptop and you can practice on it. Yeah, use the laptop.
True. Yeah.
This is the battery, okay, or you need the power, you don't have the power outlet on the table, right? Probably the battery is okay.